there, welcome to TU News. It is Friday, April 28, 2017, and we are here in Tuskegee, Alabama. I am Jocelyn Smith.
And I am Jessica Cartwright.
In today's news, we have something very exciting for you viewers to stay up to date with, and the latest, most important subject, the nanoscale materials for energy.
Today we have expert Mr. Darion Stringer, a Bachelor in Science student here at Tuskegee University, majoring in electrical engineering with a concentration in integrated circuits and semiconductors.
Whoa, that was a lot.
Yes. Well, to you, Mr. Stringer.
Good afternoon, Jocelyn and Jessica, and thank you for having me today. I'm standing here live at Tuskegee University in front of Luther H. Foster Hall School of Engineering. I'm here to enlighten your viewers about nanoscale material for energy. Nanoscale material for energy is a broad subject, so we're going to take it slow and we're going to talk about the nanotechnology side first. Nanotechnology, in simple words, is to make things smaller, allowing us engineers to make extremely small items such as implantable devices. This allows engineers to fit more technology into a chip. Physics behave very differently at a nanoscale, and we can utilize these new physical properties to develop technologies and products that will be impossible to make without the nanotechnology. For example, here are some of the everyday nanoscale and nanotechnology real-life items. The first application is aluminosilicate nanoparticles, which can stop bleeding in a hurry. Nosebleeds can last for hours, but a bandage that has been infused with aluminosilicate nanoparticles can stop them almost immediately. Their inorganic specks, which are derived from kaolin clay, triggers the body's natural clotting process. For years, doctors have used the same substance to test their patients' blood clotting abilities. Gold nanoparticles make pregnancy tests easy to read. When a woman gets pregnant, her body immediately starts making hormones called HCG. As a potential mother urinates into a sample collection area, some of the antibody-coated gold nanoparticles will migrate to the paper and into the indicator line. And if the hormone chemical is present in her urine, all of the pink nanoparticles will drift up the strip, past the pregnancy indicator line to a second marker to let the mother know that she is pregnant. Semiconductor particles make printing solar cells affordable. Solar cells are expensive in parts because they are hard to make. Most of them are produced in a vacuum chamber that use tons of energy to deposit thin layers of semiconductor materials on a wafer, such as a solar panel. Composites keep beer fresh. To cut down on the calamity, plus reduce manufacturing costs, some beverage companies have turned to exotic materials, such as clay nanoparticles, which allow Miller Brewing to bottle its beer in plastic containers. The tiny reinforcement keeps oxygen out and holds carbon dioxide in, which prevents the brewed beverage from spoiling. Those are some just real-life applications that you can relate to with the use of nanotechnology on a nanoscale material. I wanted to show you a real-life application of the meter scale. As you can see, the scale starts from 1.0 nanometers nucleotide, which simply means DNA, 0.2 nanometers at an atom, and 1 centimeter at a full blood vessel. And that was just so you can all get a visual of the nanometer scale.
So, Mr. Stringer, if I may interject, you talked about some advantages of nanoscale materials for energy and gave us a nanometer scale. What are some nanoscale materials for energy applications that some of the viewers at home can relate to?
Jessica, well, if you want to discuss the applications, there are some more applications I would like to share. For example, how photons are converted into electrons that causes us to have such energy. The solar cells that you see on calculators and satellite are also called photovoltaic cells. Photovoltaic cells, which as the name implies, photo meaning light and voltaic meaning electricity, converting sunlight directly into electricity. A group of cells connected electrically and packed into a frame are called solar panels. Photovoltaic cells, also known as PV cells, are made of special materials called semiconductors, such as silicon, which is currently used most commonly. Basically, when light strikes the cell, a certain portion of it is absorbed within the semiconductor materials. This means that the energy absorbed, light is transferred to the semiconductor. The energy knocks electrons loose, allowing them to flow freely. Some benefits within the use of PV: it requires less land than mining fossil fuel. It's clean and it's abundant. It can get more energy from the sun in an hour than we can in an entire year. Some challenges are oil and coal are still cheaper, and we can still use these materials for energy. So manufacturing materials can be quite expensive. The PV must be able to store energy for the night and cloudy conditions, and many cells contain toxic chemicals. Those are some of the challenges, but here's a brief flow chart of the process from nanocrystal synthesizing process to ink formulation to film coating, dipped into some solution, and that's what gives its final touch.
Okay, thank you, Mr. Stringer, for that well-explained application.
Perfect. And I too have many more questions for you, Mr. Stringer. So you talked a lot about this photovoltaic cells and the light absorption for the energy. Is there something that you can let our viewers know about how long we have been using this solar energy?
We have been using solar energy since forever. Starting in 7th century BC, we used magnifiers to set things on fire. In 3rd century BC, Romans used parabolic mirrors to light torches. But to further with that topic, we have different generations of solar cells. The first generation is silicon-based solar cells. Some advantages of the first generation is high power conversion, long-term stability, and some disadvantages are high cost of materials and fabrication process. The second generation is the thin film solar cell. It has a high absorption coefficient, inkjet printing, roll-to-roll fabrication, as a low-cost substrate. Some disadvantages are contamination from fabrication processes and the rare materials such as selenium and indium. Third generation organic solar cells have dye-sensitizer solar cells and polymer solar cells. And the polymer solar cells consist of organic materials, solution process, simpler fabrication process, and it has a lower cost. An example would be the solar window. But some of the disadvantages are the liquid electrolytes, which controls the low temperature and long-term stability. Polymer solar cells are solid active layers. They're lightweight and high flexible. They have a high transparency, and it has ink printing in large areas and low fabrication. Some examples of this is the military tent and portable electrode. Nanomaterials can lead to energy saving through weight reduction or through optimized function. For example, plastics or metals with carbon nanotubes will make airplanes and vehicles lighter and therefore help reduce fuel consumption. Nanoscale carbon black has been added to modern automobile tires for some time now to reinforce the materials and reduce rolling resistance, which leads to fuel saving of up to 10%. Nano-optimized lithium-ion batteries have an improved storage capacity as well as an increased lifespan and find use in electric vehicles. For example, fuel cells with nanoscale ceramic materials for energy production requires less energy and resources during manufacturing. Nanoscale materials for energy allows nanotechnology to innovate and could impact each part of the value added chain in the energy sector, such as energy source, energy conversion, energy distribution, energy storage, and energy usage. And that's the future of nanoscale material for energy. In closing, we discussed some key developments. I showcased some recent and current progression, including materials, physics, chemistry, electrical engineering, and biology. We discussed the future direction of where nanoscale materials for energy will be, and I want to thank you again for having me today. Au revoir.
Thank you again, Mr. Stringer, for sharing your expertise about nanoscale materials for energy and for sharing all your valuable information with our viewers.
Right, I know we learned a lot, so I hope our viewers really got all that valuable information.
Yes, because I learned quite a lot about photovoltaic cells.
No, it's the photovoltaic cells, as well as the photons and even the electrons. I mean, it's a lot of information, guys.
Yes, and don't forget we also learned quite a lot about current development and future direction of nanoscale materials for energy.
Right, so again, thanks for tuning in to TU News. I am Jocelyn Smith.
And I am Jessica Cartwright.
Good night.